So today, M is going to be a closed-oriented irreducible three-manifold. And I'm going to have a flow phi on M, a pseudo-Anosov flow. Let's briefly recall what this means. Well, so a pseudo-Anosov flow has the property that the first return map to a point, a fixed point, has this sort of attracting, repelling dynamics. And so the first return map looks something like this, and maybe plus or minus. And for a pseudo-Anosov flow, you're allowed to have some slightly more complicated kinds of singularities that look kind of like this. You're attracting along some number of directions and repelling along some other directions. Okay. So you have the first return map to along one of these singular orbits has this attraction repelling dynamics, possibly a rotation afterwards. So plus rotation by, say, P over Q times 2 pi. Okay. So the question I want to ask today is, does there exist a foliation? By this I mean a codimension 1 foliation on M transverse to phi. Okay. Okay, and maybe pseudo-Anosov flows actually come in families, so I also want to ask the question, well, if you modify the pseudo-Anosov flow by doing gain surgery along a closed orbit, well, how does the answer change in these families? So the main thing I want to tell you today is that the answer to this problem is computationally accessible. Okay, so both constructions and destructions. Okay, the main tool today is going to be Markov partitions. So, essentially, we're going to take this foliation and put it in nice position relative to a Markov partition. Okay. So maybe I can give you a bit of motivation for why you might be interested in this kind of question. So there's a conjecture, I guess we'll say it's due to Thurston, that if S is a foliation, a taut foliation on M, let's say M is atoroidal, then there exists a transverse, or there exists a flow phi transverse to F, and this flow is either periodic or pseudo-Anosov. Okay. As written, this isn't quite correct. There's another adjective you have to put in here, almost transverse. But let's just forget about this almost for now. Okay. So foliations give rise to pseudo-Anosov flows. So maybe if you sort of believe in this program, then one sort of strategy to understand all the taut foliations on your manifold is to first classify the pseudo-Anosov flows, and then two, classify the foliations transverse to the pseudo-Anosov flows. Okay. All right, so what's known about this conjecture? Well, in the fibered case, so if F is a fibration, this is the Nielsen-Thurston classification. Okay, so given a fibration of a 3-manifold, there exists a flow that's transverse And that flow, well, is either periodic or pseudo-Anosov. Yeah, sure. Okay. Thurston proved this for a more general class of uniform foliations. This was generalized further to R-covered foliations. By Henley and Caligari. And also finite depth foliations. This is due to Dave Gabay and Ling Mosher. Okay. But the conjecture is open in general. Okay. Okay, so let me say a few words about this program in the fibered case. So in a fibered case, it's very easy to understand all the fiberings transverse to a given pseudo-Anosov flow. So say phi is a pseudo-Anosov flow. Then the fiberings of M transverse to phi, these guys are in one-to-one correspondence with elements alpha of first cohomology of M, such that alpha is positive on all the closed orbits. Of phi. Okay. So, given a cohomology class like this, there's a representative such that its kernel is a fibering of M, and that fibering is transverse to M. Okay. So, turns out there are a finite number of flows transverse to fiberings on any given 3 manifold, and each of those flows corresponds to one of the faces of the Thurston norm ball. And so this single pseudo-Anosov flow sort of organizes a whole bunch of different fiberings of your manifold. Okay. So one thing we learned from this example is that these pseudo-Anosov flows are kind of a more rigid object than the foliations, the fiberings. So maybe it's easier to first understand this kind of rigid problem of classifying all the pseudo-Anosov flows, which are really combinatorial objects, and then later to try to understand the more flexible question of understanding all the foliations transverse to one of these flows. Okay.
Phi here is the suspension flow, right?
Yes, that's right. So if I have a particular fibering, then the fibering will be the flow phi will be the suspension flow. Okay. So before talking about this question, maybe I'll remind you some things about the ciphered fibered case. Okay. So let phi be a periodic flow. So in other words, a ciphered fibration. Okay. In this case, there's a sort of a classification of the top foliations on 3 manifolds like this. So we'll have M, a ciphered fibering over surface sigma. Okay. And maybe I'll say things about a few particular examples. Well, sorry. Maybe I'll first say the theorem of Thurston and Krishna. Theorem. Any top foliation F on M can be isotoped to be almost transverse to phi. Okay. Here, almost transverse just means that that each of the leaves are either honestly transverse to the flow phi, or they're saturated by ciphered fibers. Okay. So again, you can kind of forget this almost adjective here. So understanding all the foliations on a ciphered fibered space reduces to understanding all the so-called horizontal foliations. Okay. So foliations of M transverse to phi are in one-to-one correspondence with representations of pi1 of your surface, sigma, into homeo plus of S1. And representations with the right Euler class. Okay, let me write down some particular examples. So, example 1. Let's take the case when the base is some surface of genus G. And we'll have a single singular fiber. And we'll do sort of P over Q surgery here. So the space I want to think about is sigma G cross S1. And we'll do Dane surgery with slope P over Q on one of the singular fibers. Okay. In this case, the foliation is transverse to our flow phi are in one-to-one correspondence with choices of some elements of homeo of the circle. Such that this product of commutators is AI BI is equal to a rigid rotation by P over Q. Okay. Example 2 that you should think about. This is the case of a small Seifert fiber base where your base is S2. And you have 3 singular fibers. And so we're looking at S2 cross S1. And we're doing Dane surgery along some fibers with slopes P1 over Q1, P2 over Q2, and P3 over Q3. So this time we can also rewrite the problem of existence of foliations in terms of a problem in one-dimensional dynamics. So transverse foliations are in one-to-one correspondence with choices of elements A and B in homeo S1. Such that AB A is a rotation, rigid rotation by P1 over Q1. B is a rotation by P2 over Q2. And AB is a rotation by minus P3 over Q3. Okay. Questions at this point? Okay, so both of these problems are completely solved. So in the first case over here, the solution to this problem is given by the Milnor-Wood inequality. And Milnor-Wood inequality says that there exists a foliation if and only if P over Q is pretty small relative to the genus. So the takeaway here is that if you have sort of higher genus on this surface, that gives you a bit more flexibility with changing these, for making these foliations. Okay. Over here, there is also a complete description, but maybe I won't tell you the precise description of this set. But there exists a foliation transverse to this Seifert fiber ring, if and only if this triple P1 over Q2, P3 over Q3 lies in some set that I'll call Z in R3. And Z is a neighborhood of the set P1 over Q1 plus P2 over Q2 plus P3 over Q3. Okay. So Z is a proper subset of R3. It contains the abelian representations of pi1, but it also contains things a bit farther from the abelian representation. So in this situation as well, there's some sort of flexibility in constructing these foliations. Okay. Maybe I'll show you a picture of this set Z. Oh, do I have to click something? Okay, so this is the set Z, and you can see there's some sort of Diophantine phenomena going on. So the set, the abelian representations lie on this plane, and we're able to perturb a little bit away from the abelian representations to get some sort of interesting foliations. Okay. Questions about this picture? So this picture is R3. Each point in this picture, well, inside the green set, represents a tuple of slopes of the PIs. And a point is inside this set if and only if there exists a foliation transverse to the periodic flow. Okay. Questions about this picture? Okay, good. So what I want to tell you today is that we can do a similar sort of thing for flows, for foliations transverse to pseudo-Anosov flows. Okay. So let's look at the pseudo-Anosov setting. Where phi is a pseudo-Anosov flow. Okay. And again, we can make the same sort of setup. So I'm going to start with a fiber 3 manifold. So fibering over the circle with pseudo-Anosov monodromy. And phi is going to be the suspension flow. And we'll choose some closed orbit gamma of this flow. And I want to do Dane surgery along gamma, just as I was able to do Dane surgery in the periodic case. So we can do Dane surgery along gamma. Okay. So one thing to know about pseudo-Anosov flows is that they often survive Dane surgery. Okay, so here's the picture. If you take your closed orbit gamma, you can blow up this orbit. Delete the orbit and sort of, get a flow on a 3 manifold with torus boundary, equipped with a flow which is tangent to the boundary, and the flow is mostly going in the vertical direction. So then you can do a Dane surgery by filling in along some new curve here and get a new closed manifold with at least a topological flow. Okay? On the other hand, foliations often don't survive. Okay. So if I have some closed orbit gamma with a foliation by leaves which is transverse, after I do a Dane surgery, each of these transverse leaves will become some sort of surface that's spiraling around like this. Okay. So what you get in the end is something we'll call an open book decomposition. Or more generally, a confoliation or a contact structure. So if you do positive gain surgeries, then you're making some sort of positive twisting in the resulting two-plane field, and you're getting a contact structure instead of a foliation. Okay. So something that Rachel Roberts taught us is that these vibrations actually sometimes do extend to the gain surgeries. So Roberts. So vibrations can be perturbed to survive small gain surgeries. And actually, she was able to give some concrete bounds, like you can go maybe do a single positive gain twist. Okay. Roberts and Lee generalized this theorem to finite depth foliations as well. So you can do gain surgery along a small positive gain surgery along a transversal to a finite depth foliation. What Thomas taught us today was, earlier this week, is that actually for any foliation with a transverse curve, we can do some small positive or negative gain surgeries. So foliations survive gain surgery. Well, small gain surgeries. Okay. So the question I want to ask today is, how far can you go? Can you do really big gain surgeries, and can these foliations still survive? Okay. Questions at this point? Yep.
So, like, if you want to test something doesn't survive, do you require the new foliation to be C0 close to the old, like close homotopic to the old one, or you just
yeah. So I'm just asking if there exists a foliation. Okay, but in practice, yes. In some sense, it's close to the original.
You said that usually foliation don't survive. You mean we don't know that there's an obvious way of extending?
That's correct. That's correct. There's no obvious way for to perturb this foliation. Any other questions? Okay, so to kind of attack this problem in a similar way to the way in which we attacked the separate fiber case, we want to reduce this problem of the existence of foliations to a problem in one-dimensional dynamics. Okay?
Actually, can I ask a question?
Yep.
Coming back to that question.
Yep.
So, like, this picture is really sort of optic semi-conjugacy, is it?
I'm not sure what you mean by.
Like each point of this picture gives you I just wonder,
uniqueness. I'm only claiming existence. Yeah, I'm only claiming existence right now. Okay. Yeah. Okay, so maybe I'll stay with, I'll prove what the corresponding problem in one-dimensional dynamics is. So I'm going to do this example that Rachel had in her talk. We have this pretzel knot, P minus 255. This is a fibered knot in S3, fibered hyperbolic. And so the complement of K emits a pseudo-Anosov flow. Okay. So we can ask, for which gain surgery does this natural fibration extend, or can it be perturbed to a foliation on, on the gain surgery? Okay, so here's the problem in one-dimensional dynamics that includes that problem. So in this picture, you have a whole bunch of variables, some of them A's and some of them A inverses. This picture is actually a torus. It's naturally living on the boundary of the complement, S3 minus K. So how do you interpret this problem? I'm looking for a substitution of an element of homeo of an interval for each variable. And once I substitute a homeo for each point here, I can construct a lamination on the plane, on the torus. So this gives me a lamination on the torus. So how does this work? So you'll notice that at each of these junctions, you have a bunch of incoming branches and some outgoing branches. And so you're supposed to thicken up this picture so that each of the edges is trivially foliated. And at each of the junctions, you have some incoming bundles and some outgoing bundles. Okay. And inside this junction, you insert an element of homeo of an interval. Okay. So we get some sort of foliation on this torus after you blow down the complementary regions. And the question is, what slopes can they achieve? Question. What slopes are achievable? Okay, so here are some facts. So let Z be the set of achievable slopes. And so here's fact 1. Z is a connected interval in R. Maybe 2 is specific to this example. Actually, Z is a subset of -4, 4. Okay. Maybe I'll try to convince you of this fact. Well, let's suppose there was an assignment of a homeo to each of these variables so that you had a really large slope. Well, how could you achieve really large slope? You'd have to run along this left-hand edge of the picture for a long, long time. Okay? And in particular, you'd run into both C inverse and C. Okay? So somehow, if you chose C to be a very ascending homeo of the interval, then C inverse would be a very descending homeo of the interval. And that would kind of prevent you from traveling with a very large slope in this picture. Okay, so in this case, Z turns out to be a proper subset of R. Okay, questions about that? Okay. Okay, so what's the point of this problem? Well, there exists a foliation on the same surgeon.
Slopes is defined as the set of slopes that are carried by that train track? Or?
Yes, the set of slopes that you could achieve by substituting each element with a homeo at the interval. So it's not the same as just all the slopes that can be carried by the train track. There's this condition that you have the same. Well, if you substitute a homeo at A, then you have to substitute the inverse homeo at A inverse.
Now you have the whole lamination. What slopes, given the lamination, are achievable? Once you have the lamination, how do you read the achievable slopes? Is that like the set of closed loops of that lamination, or the whole lamination should be more specific?
So once I fix a sort of picture like this, I'm looking at the slopes that are achievable by, sorry. So really, it's not a it's an honest, you can be blown down to an honest foliation, and a foliation really has a slope. Okay, so there's no choice once you've made this choice of the homeo at each interval. Okay. So 3 facts. There exists a foliation on the Jane surgery if and only if S is on the interior of Z. Okay. And this is proved using Massoni's result. Okay. So we've sort of reduced the problem of understanding foliation transverse this pseudo-Anosov flow on this problem to this problem in the one-dimensional dynamics. And in particular, we can show that there are a whole bunch of pseudo-Anosov flows that don't admit transverse foliations in this case. Okay. So maybe I'll say 4. In this case, there exists an algorithm to check whether a given rational slope, P over Q, is inside is inside Z. Okay, so this is the sense in which this problem is computationally tractable. Okay, so let me say that this setup also works for many Cupst manifolds. So this works for multiple boundary components. Okay. But maybe I won't say specifically what the setup is. I want to say maybe a very brief word about how you come up with this picture here. So the main idea is to put F in good position relative to a Markov partition. So let's recall what a Markov partition of phi is. It's a set of rectangles transverse to the flow. Their boundaries should be parallel to the stable and unstable foliations of the Anosov flow. So half of these boundaries lie inside the stable foliation, and the other half lie in the unstable foliation. And we have some more data associated with the Markov partition. There's a decomposition of the complement M minus the I's into flow boxes. And I'll say into proper flow boxes. So it's a proper flow box. It's a subset of the manifold that's saturated by flow lines, and sort of looks like something like this. It has one face on one of the rectangles, and another face on top face on one of these other rectangles, and it's expanding in one of the directions and contracting in the other direction. So proper means that the top is full width, and the bottom is full height. Okay, questions about the setup here? Okay, so here's the main proposition. Given a top foliation F transverse to phi, so if F is foliation transverse to phi, then can modify the Ri's so that each flow box is trivially foliated. Okay, so I want this flow box to just have a bunch of leaves that are all horizontal. Okay, in particular, all the rectangles should lie on leaves of the foliation. Okay. What do I mean by modify? Well, I'm not going to really modify the combinatorics of the Markov partition, but I'm going to allow myself to move these rectangles up and down along the flow. Okay. So if you believe this proposition, then the existence of a transverse foliation is really about this problem of taking some trivially foliated flow boxes and gluing them together so that the foliations match up. So the combinatorics of that is what's described in this picture here. That, okay, so maybe I won't say any more words about the problem in one-dimensional dynamics. So my promise was that I would show you some pictures of these set Z. So I'm going to look at some manifold M with two cusps and some pseudo-Anosov flow phi on M. Okay? And we're going to consider this family of Dane fillings with slopes S1 and S2. And so these Dane fillings, phi, let's see, so phi usually extends to the Dane surgery, M of S1, S2. Okay. So I'm going to define this set Z in R2. That's the closure of the set of slopes. Closure of S1, S2, such that phi M of S1, S2 admits a transverse foliation. Okay, so here's this plane R2 that I'm talking about. And what I drew in blue are all the fibrations. So there exist some slopes, S1, S2, such that when you extend to the Dane surgery, there's actually a fibration transverse to the pseudo-Anosov flow. Okay, so generically, this is a codimension 1 subspace of the plane. And actually, it has some endpoints. So really what you're looking at here is the incarnation of one of the faces of the Thurston norm ball for the complement, or for this two-cusp manifold. Okay. So here's this set Z. So you can see, you can kind of perturb a little bit away from these fibered guys. So there are these slopes that are pretty close to the slopes admitting fibrings, for which you can actually still construct foliations. So these foliations are constructed thanks to Thomas's result. But you can't get everything. Okay. So theorem, in the far upper right corner and the far lower left corner, there are actually no taut foliations. This we know rigorously. Okay, so that's analogous to this fact that we can't get extremely large or extremely small slopes. Maybe there's one thing to say. Well, what Rachel and Thomas proved was that if I start with one of these foliations, for example, one of these blue foliations, I can perturb a little bit. I can get slightly bigger and slightly smaller slopes. But you'll notice that there's one special foliation in the middle of the picture, some special fibering that doesn't perturb at all. It seems to be living on the boundary of Z. And this seems to be at odds with what Thomas proved. So actually, I brought in this picture to show Thomas, and I complained, and I said, hey, I found this counterexample to your theorem. So here's the pop quiz. What's happening at that little point in the middle of the picture? There's a fibration that's not not perturbing to give taut foliations on any small Dane surgeries. Yeah.
Is S2 for this one?
Yes, very good. So it's our favorite, three manifold towards the Elias-Thurston theorem doesn't apply. So S1 plus S2 is this.
Therefore, it's not our favorite. In fact, it's the opposite.
Yes, it's our sort of least favorite, but it's still, it still deserves to be called a taut foliation somehow. It's just the most rigid foliation. Okay. So what I wanted to explain to you is that so we learned from the Milner-Wood inequality that high genus means more flexible, low genus means less flexible. So what you're seeing is that these very inflexible points are these fibrations with very low genus. Okay. You'll notice some other things about this picture. The corners here appear to be rational numbers. Okay, so this is the point minus 2.5. And I don't know how to prove this in general, but this is actually something that's conjectured by Caligari and Walker in the Seifert fibered case, and in their related problems. They conjectured that all the corners of this picture are rational numbers. And in fact, there's also these sort of special points where the corners are accumulating. And they call these the slippery points of the ziggurat. So I think they're called slippery because if you're climbing on the staircase, those are the places where you're liable to slip and fall. And so I guess they make some conjecture about these points. And in particular, one of the conjectures they have about these points is that these points lie at abelian representations. So these, in the language here, these special accumulation points of corners of the ziggurat should lie at these fibered points, and in particular at S1 cross S2. So maybe here's a conjecture. P is slippery if and only if S1 cross S2. Okay. Maybe something I'll say about this picture. Previously, this is only actually a lower bound for the set Z. And so actually, I haven't proven that there are no, Z isn't any bigger. I've only proven that in these far quadrants, over here to the upper left, over here to the upper right, and over here, there are no foliations. Okay. So you might ask, well, can I sort of, so why do I think that this is the maximal, this is the set Z? Well, there's a naive generalization of the Milner-Wood inequality to the pseudo-Anosov setting. So the Milner-Wood inequality roughly says that you can't go too far from the abelian representation, and the distance from the abelian representation that you can go is roughly related to the Euler characteristic of the fiber. So here's the naive extension of Milner-Wood. So let's suppose I have a point on this picture, P1 over Q1, P2 over Q2. And this is a fibering. And let me cap off on this side. And okay, so let me say, let's let chi be the Euler characteristic of the fibering after capping off the second component, the second cusp. Okay, so we're going to do sort of zero surgery along the second cusp. And the naive generalization of the Milner-Wood is that P over P1 over Q1 plus chi, P1 over 2 is not in Z. Not in the interior of Z. Okay. So this is maybe I'll have the caveat that the absolute value of chi is less than the absolute value of Q1. Okay. Okay. So every point in this on this picture is supposed to give me a constraint on Z. And so here's the union of all these points, red points. So each of the blue points gives me a pair of red points, one directly above it and one directly below it. And in particular, there are some special red points here sitting at these corners. Okay. So my claim is that these red points are excluding all top foliations to the, below and to the left of them. Okay. Okay. So it would be great if someone proves this inequality here. Yep. Anyway.
Sorry, do you mind saying quickly just what green, purple, and red mean?
Yeah, sure. So purple are the fibrations of, well, there are certain slopes for which a fibration of M extends to a fibration on M1 cross on the Dean surgery. Okay. So there's a one parameter family of fibrations of the 2-cusp manifold, and there's a boundary map that goes from fiber surface to just some slopes. And if you fill along those slopes, well, you obviously get a foliation. Okay. The greens are taut foliations. Okay, so we can sort of get a little bit farther away. Okay, maybe one thing I forgot to say about this picture. Something great that Thomas proved is that if you have 2 points in green, say here and here, then actually you get all the points below and to the left of the upper corner, all the points in the rectangle whose lower left corner is in green and whose upper right corner is in green are also in green. So the set green has some sort of monotonicity properties. Okay. Okay. Any other questions about this picture? Yeah.
When you say the foliation, you mean the foliation transverse to the flow?
Yes. Yes, transverse to the flow on the surgery.
And you know if there are other foliation like that are not maybe?
That's right. So I'll remark that, in fact, in this example of the pretzel knot, P minus 255, we know that there's no foliation on some interval containing the so-called degeneracy slope. But in fact, there's another pseudo-Anosov flow on the complement of P minus 255. And if you construct this set Z for this other pseudo-Anosov flow, in fact, Z is the entire real line in that case. So in fact, it's actually fairly easy to find these other pseudo-Anosov flows. A good strategy to find them is to take the complement of this knot, drill along a short geodesic, and usually what you'll find is that after drilling along some short geodesics, you'll find some fibered manifold supporting a new pseudo-Anosov flow, and then you can try to run this kind of picture here. Any other questions? Okay. So maybe I'll just show you a few more examples of these kinds of pictures, show the kinds of phenomena you see. Right, this region Z is usually not bounded. Here I drew some different sized circles and the sizes of the circles are demonstrating the Euler characteristic of the corresponding fiber. So smaller Euler characteristic means a bigger dot. So what you sort of see is that these big dots. Right. Okay, maybe I won't say anything about the Euler characteristic in this case. Okay, so in sort of all these cases, if you have a little red dot sitting at all of these concave corners, then you've sort of proven that this picture is complete and correct. Okay. Okay, so here's another example of what you can see. Sometimes you have these knots with these links with 2 S1 cross S2 surgeries. And so in these cases, you'll see 2 of these so-called slippery points. And near these points, we actually expect that there's a sort of infinite staircase that's approaching this S1 cross S2 surgery. Yeah, okay. So, but away from the S1 cross S2 surgery, you can really perturb away from the fibered locus. Okay. Okay, so maybe now I can explain this picture I showed yesterday. So this is an example of the set of, this picture shows the geography of all the Dane fillings on some 3-component link. Okay, what's the link? Maybe I have a picture of it up here. This is kind of a famous link. this minimally twisted 3-chain link, it has, its complement has, is expected to have the smallest hyperbolic volume among all three among all three hyperbolic manifolds. Okay, so in fact, you see the same sort of picture, you see these sort of accumulation points. And in fact, all these accumulation points of the corners of this so-called ziggurat are at S1 cross S2 surgeries. So maybe I'll show you all the S1 cross S2 surgeries in the picture. Okay. So in fact, for this link, there's a whole one-parameter family of S1 cross S2 fillings, and they all lie along this, this sort of hyperbola shape. But then there are also these other kind of interesting S1 cross S2 surgeries. So the conjecture is that all of these points are accumulation points for the corners of Z. Okay, maybe I'll stop here.
Thank you. Questions?
Yeah.
For this lamination slope, so I guess like there's no, you cannot have irrational rotation number, right? So you assume it's rational rotation number.
That's
and you
right.
pick any closed orbit of that, and they all have the same slope. Is that how it's defined?
That's right. I mean, in fact, I mean, of course, you can construct irrational slopes, but they don't really mean anything.
For construction.
Yeah. Yeah.
Are there any other questions? All right. If not, let's thank Jonathan again.